SwayamPrabha. Digital India. Educated India.
We are going to start a new topics today, and that is on spinodal decomposition. This topic is little new to you because normally spinodal decomposition is not taught in many of the BTech curriculum and across the country. So I request you to be very attentive and listen the things very patiently. Obviously, we cannot talk every details of this transformation, but I will try my best to put things together so that you understand what is it. It is a decomposition, so that means some phase transform to other phase or more than one phases. So product phase transform to more than one product phases. So it is a decomposition. Just like if you take a material, heat it inside a furnace, it can decompose into different phases. Similarly, same thing happens or not, that needs to be seen, but it is a decomposition in that way. Now, what kind of decomposition it is? As you know, this is observed in very peculiar phase diagrams. The phase diagrams which shows the free energy versus composition diagram, the one like shown here. We have discussed the quasi-chemical theory some time back as a part of this course, and in that quasi-chemical theoretical approach I discussed that depending on the type of interaction between these solvent and the solute atoms in a solute solutions, different kinds of free energy versus composition diagrams exist, and the one which is very distinct and different from the normal solute solutions is the one in which the free energy versus composition diagram shows a hump, just like a road bumper. So you can clearly see that free energy initially was like this, then it decreases, then it passes through a minimum, again increases, reach a maximum value, decreases, again increases. So as you go from pure A to pure B ends, only at both the ends the free energy is decreasing initially as the composition of this solute increases. As the composition of B increases, the free energy is decreasing, but then there is a composition beyond which it starts increasing and reaches a maximum value. That is why I say it shows a hump. Now whenever you have such a kind of situation, this happens only when the interaction between similar atoms are stronger than the dissimilar atoms. What does it mean? In a solute solution, suppose you have A and B type of atoms. So there are three different types of interaction one can have: interaction between A and A atoms, B and B atoms, and A and B atoms. Okay. So the first two interactions are similar type of atoms, atomic interactions, and the last one, that is between A and B or B and A, they are similar. This is dissimilar type of atomic interactions. Now if in a solute solutions the interaction between similar atoms are stronger than the dissimilar atoms, so what will happen? The solute solution will be not exactly solute solution, but it will remain as a cluster of different similar atomic pieces. AA will be more preferred than AB, similarly BB is more preferred than BAB. So therefore system will like to have more AA and BB bonds than AB bonds. It is energetically favorable. Such situation will give rise to this kind of free energy curves, which will come very clear later on. Now if you have such a kind of free energy curve, we can use this free energy composition diagrams to generate phase diagrams. We know that. Normally we, in the lectures we do other way, we just show you free energy composition diagrams when you know the phase diagram. But normally free energy composition diagrams obtained at different temperatures can be utilized to generate the phase diagram. Now here the phase diagram is shown at the top. Okay, so let us first look at the solid line of the phase diagram. So because of the presence of this kind of hump in the free energy composition diagram, okay, you can see that it shows a dome shaped structure. Okay, it just goes up and then goes down. It is dome shaped structure. Now such a kind of phase diagram is a signature of what is known as spinoidal decomposition. Let us explain in detail what actually happens. Given that you know the phase diagram exists, only I am asking you to concentrate on the solid line. Okay, do not look into other parts now, which will be coming slowly. So now suppose if I take an alloy composition, alloy of composition x0, that is what is dotted line shown. So at T1, this alloy of this composition x0 will be a complete random solid solution of alpha. Okay, that is shown there. Now as we cool down this solid solution alpha, suppose to T2, let us suppose we quench instead of cooling, because now you know what is quench. We have discussed a lot about quenching martensites in steels. So let us suppose I take this alloy, quench from T1 to T2. Correct. As you see, as T2, that is what is written, at this temperature alloy will be having a free energy given by G0 here, you see there, because this is also composition axis, this is composition axis. So I can x0, it will have a free energy of G0, you can dotted line can be drawn and so on. So now question is this, at this temperature this solution is not stable. Why? That is observable clearly from the free energy versus composition diagram. Why it is so? It is very clear that even if there is a small fluctuations, smallest possible fluctuation, let us suppose, of composition in this solution alpha at temperature T2, these fluctuations can grow. Why? Okay. First let us see that. Suppose as I told you, the free energy of the solution at temperature T2 is G0. Now if it decomposes into two phases of composition, suppose one having composition given by this point, other one is this point, and we have shown there is a line joining these two. So therefore the free energy of that solution G0 can be reduced to G1, okay, here you can see here G1, okay, by decomposing into two solutions, this one and this one. You may ask, sir, how? Say if I have two solutions, one has a composition of this one and other one has a composition of these two, because of decomposition of this solution alpha into two different solutions, composition of this and this. Now what will happen? The average free energy value of these two phases is given by G1, that must lie on this line. That is obvious, because average is what? Average is nothing but free energy of this multiplied by the mole fraction of that, and free energy of these multiplied by the mole fraction of that. That is what it is, or mole fraction of that rather, not mole fraction. So this will lie on this line and this will be just below this, because the composition of the solution, initial solution was x0. But if you look at carefully, it can still decompose, keep on decompose like this, okay, and two different solutions can be produced. So what is the meaning of that decomposition? The decomposition will happen in such a way, it will produce a phase which will reach in A, produce another phase which will reach in B. That is what you see here, this one, reach in A, reach in B, reach in more A, reach in more B, reach in more A, reach in more in B. Slowly this will happen. Now this process will occur for any alloy compositions, this process, spontaneous process will occur with any alloy compositions for which this condition is satisfied. What is that? The double derivative of G with respect to the composition must be less than 0. That means that equivalent to saying that this will happen till this inflection point on this curve. What is that inflection point? As you see here, this one is one curve, that one is another curve, right. You see, if I draw it here, this is one curve, this is another curve, part of the same curve, but this is concave, this is convex. So, there is an inflection point. What is inflection point? Inflection point is where the curvature is changing. The curvature is always given by double derivative. You know, the slope is given by single derivative, this one is slope, okay, and this one is tells you the curvature. So, as you see here, curvature is changing from negative to positive. I do not know, but anyway curvature is changing, does not matter whether negative to positive, but this changing. So, when it changes from or changes a sign, there must be 0 point. It cannot go through directly from positive to negative or negative to positive, but there must be. So, that is why these points are shown as a double derivative equal to 0. So, this decomposition which is happening spontaneously leading to two phases A reach and B reach can easily happen without even requirement of nucleation. This is something which is not easy to understand. This is a spontaneous process, does not require any nucleation, and so corresponding to these points we can draw another curve. So, that dotted curve which is shown here is known as chemical spin-order, and that means any alloy composition within this range will undergo decomposition, as I just now told you, spontaneously decompose into two different phases at temperatures below this. Okay. That is what is known as spinodal decomposition. I hope I am clear to you, understandable to you also. The whole process which I described you just now, thermodynamically as well as using phase diagram, is known as spinodal decomposition. Remember, this is one of those processes, very few, where you do not need nucleation of the second phases or parent phases. The composition fluctuations, whatever exists in the material, grows spontaneously, and this happens within the chemical spinodal decompositions. So, now question is that, will it stop here decomposition? No. Why? Because you see here, still it can reduce the free energy till these 2 points, okay, reaches, then only the free energy is increasing as you increase the composition. So, till this point here you see these two are, till these points the chemical decomposition will keep on happening. So, finally, any alloy will decompose into A and B rich compositions given by XA1 and XA2 at temperature T2. But alloys whose compositions lie between chemical spinodal and this solid line, here also between chemical spinodal and the solid line, they will undergo nucleation and growth. This kind of decomposition will happen, but it will happen via nucleation and growth. Okay, so any alloys outside this chemical spinodal, small variation in compositions will lead to increase in free energy. Okay, and the alloy therefore is metastable. So, if the free energy system can only be lowered or decreased if a new nuclei of the new phases formed with a small, with a composition very different from the parent phase. Therefore, outside the spinodal decomposition, transformation must proceed by nucleation and growth, and normal downhill diffusion, just now I discussed with you downhill diffusion will happen. See why it is called downhill diffusion? Normally diffusion will happen down the concentration gradient. So, therefore, in the alloys, that is what you have seen in many of these processes, whether it is a paralytic transformation or it is any other transformation which you have seen where it requires diffusion, precipitation also, diffusion always happens down the concentration gradient, that is called downhill diffusion. But within this chemical spinodal, diffusion happening uphill. Why? Because the alloy is having this composition X0, as you see here X0, with certain amount of A, certain amount of B, but a decomposition in such way that A regions become more A rich, B regions become more B rich. What does mean? As you decompose into these two phases, the process of decomposition must be such that A will go to A, B will go to B rich regions, which is opposite, right? Normally A rich regions, A must diffuse from A rich regions to the B rich regions. Why? Because that is where the compositional gradient will decrease, but in this case it is happening other way. Here A rich regions, A will move more into A rich regions and B will move more into B rich region, and that is what is known as aphel diffusion. So, diffusion is happening against the compositional gradient. This is very widely accepted thing, happens in the literature. So, let me discuss some more stuff with you. Okay, so again that diagram was taken from the book of Porter and Sterling. This is taken from Jena and Chaturvedi. Similar things as you see here. So, as you see here, this is a complete phase diagram. Up top portion shows a isomorphous type phase diagram, leads to formation of the solution alpha. At temperature above Tc, the alpha is stable, it is a random solutions. Temperature below Tc, it undergoes spin-order decompositions, and everything is shown here. Inside curve is known as chemical spin-order, because that is where the transformation will happen via spontaneous decomposition, no need of nucleation. Between the spinor, the dotted line or dashed line, that is what is chemical spinordal, and the solid line, the boundary of the spinordal, nucleation and growth can happen. Okay, so that is what is shown here, phase separation by spinordal decomposition, and here phase separation by nucleation and growth. Be careful about this, and we told you why does it happen. As you grow past these inflection points, the free energy, any free energy will, decomposition will lead to increase in the free energy. That is what you see, correct. Small variation in composition will lead to increase in free energy as you go beyond these 2 points, inflection points, and that is why the only way it can reduce its free energy system by nucleation and growth. And this is basically a blown up view of that whole situation, and little more aspects which needs discussion. Okay, as you see here, this is a free energy curve. It shows a hump with the 2 inflection points, and I will just draw and then remove it, show you how these inflection points develop. See, this is a curve with this kind of slope, okay, and this is a curve with this kind of slope. So, and therefore, there is a change of curvature, okay, and this change of curvature is given by this spinor, the what is that known as inflection points. Okay. So, now let us first explain in terms of the chemical potentials, and I am going to show you 2 important points on this diagram. Let us first take this chemical potential here at the top of this dome. That means let us suppose I draw a tangent to the curve, okay, and if I draw a tangent to the curve for xu dot, this is the xu dot compositions, I draw a tangent. So, what will happen if I extend the tangent, what it will give? It will give the chemical potential, that you know. So, chemical potential means the G1 bar and G2 bar for component 1 and component 2 for a chemical composition, for a composition of the alloy xu dot. Okay, this is taken directly from the book of Jena and Chaturvedi, so I have not changed the symbols. Symbols are a little bit, not simple one by the way, but it explains the things very nicely. So, what will happen? This is the chemical potential of component 1, chemical potential of component B, correct. Now, question is this: why it will, any kind of decomposition must lead to reduction of the chemical potential, right, that we know, because chemical potential must be equal, then only this will be, the transformation will be same. So, as you clearly see, for the composition xu double prime, chemical potential of component 1, chemical component 2 is given by this. Now, so that means what? Chemical potential of 1 can be decreased this way, chemical potential of 2 can be decreased this way, correct. So that means what? That means that any alloy composition lying on the top of the dome, they can reduce the chemical potential by decomposing into 2 phases. Okay, this can go down or this can go, it can reduce easily. So you can see here, if I draw a tangent here, this will be, you can see that this is the chemical potential here, and this is, if I draw a tangent here, chemical potential will be like this. So chemical potential of component 1, chemical potential component 2, component 2, component 1. So it is getting reduced, right. So in the A rich region, chemical potential of component 1 is very low, B rich region chemical potential of component 2 is also low, correct. So similarly, if I do it at these minimum points here on this curve, you can see here x prime m and x double prime m, okay, the chemical potential are shown G2 prime, G2 x2 prime and x prime double prime. Okay, it is very clear that this is the chemical potential can be reduced farther down as you go along this. So that is the basic mode of transformations. Now before I go to the kinetics of these transformations, let me just show you few of these important phase diagrams and microstructures in next 4-5 minutes. This is I think phase diagram between nickel and cobalt. As you see here, there is a chemical potential here, chemical spin orbital here, and the spin orbital alpha is going to transform into alpha and alpha 2, and there is a coherent spin orbital which we will discuss later, maybe next class. So what is it? But that is how the phase diagram looks like. Okay, now here this is again, I think this is zinc, copper zinc probably, yeah. Now aluminum zinc, yes, aluminum zinc. As you see here again, although the boundary is so there is a chemical potential and there is a coherent spin orbital which we will discuss later. What is coherent spin orbital? As the alpha can decompose into 2 phases spin orbitally. So what are these pictures shows? These pictures shows the chemically spin orbital decomposed regions. You see here how these 2 regions form, one is this, other one is this, one is this, other one is this, decomposed regions can easily form. Okay, some of the microstructure which you will be able to see. This is also another one, it basically shows the chemical, the spin orbital of decomposition of the 2 phase, one is white color, one is a black color, the dark field image, take transmission electron microscopy, this is a copper nickel alloy, okay, copper nickel it must be, and it shows that there is compositional variations across 1O directions. This is 1O, this is 0,1O. So basically that means along the both directions the spin orbital decompositions, the fluctuation waves or the decomposed zones actually created. You can see the fluctuation waves, right. This is like this, you can draw that, increase here in the middle, decrease here in the middle, okay. But that means if you draw for white phase, this will be opposite black phase which I have drawn. So in the both sides, both direction it exists. In many cases, many of the alloys, this is iron silicon, it shows as very fine scale spin orbital decomposition structure. Okay, so this is how the microstructure looks like. These are the small domains of composition fluctuations, and these domains can then further grow and become bigger. So in a schematically we can actually show, the next slide will be showing you that. This is another one, is aluminum zinc magnesium alloy. This has been heat treated at 400 degrees Celsius and aged for 20 hours. Solution treated at 2 hours for 400 degree and then followed by aging at 100 degree for 20 hours. I see here the decomposed parts, decomposed regions. You can see that along this direction, both are present. So there is some crystallographic orientation of these decomposed zones. This is what exactly happens as you talk of the decompositions. So suppose I have alloy with a composition x0, okay. So and then it is within the chemical spin orbital regime. So therefore any small fluctuations whatever there will spontaneously develop. As you see here, these fluctuations are slowly developing. So B is these regions becoming, B is diffusing out, so these regions becoming A rich, this is also A rich, this is also A rich, and these regions are actually B rich, okay. So now slowly, as you know, slowly these regions are actually becoming bigger. So, B rich regions are becoming bigger, similarly A rich regions are also becoming bigger. These are the B rich regions, okay, and these are the A rich regions. So, I am drawing by dotted line, okay, this is also dotted, this is continuous. And finally, final microstructure will have completely decomposed regions of A and B rich. You can see here X2 and X1, correct. That is the composition zones of that. So, this is directly taken from the first one I showed you. Let me go back, this one, okay, X2 and X1, you can see here this is directly done that. So, if you do that, this kind of things will form, okay. So, now so this is the increasing time, as the time increases this one will happen. So, that is basically what is meaning of spinor decomposition. That is the way we can actually explain how spinor decomposition occurs, how it happens. Now, in the next set of lectures, we are going to discuss how the kinetics happens actually. In the book also they have given what is how the rate of transformations depends on, and whether actually we can get some analysis using the synergies of these transformations. That is what we will do in the next lecture.